Hello everyone and welcome to this data science crash course. My name is Marco and I just recently started a YouTube channel where I do videos on data science. So if you want to check it out, the link is in the description below. A bit of an overview of this crash course. We will first answer the question, what is data science? Then we will walk through a setup so that you are ready on your computers to code along with me. And then we will move on to the algorithms, which is, in my opinion, the fun part. So we'll talk about linear regression. Then we will move on to classification with logistic regression, LDA, and QDA. We will talk about resampling and regularization methods, which are very important in any workflow for a data scientist. We will talk about decision trees. Most of the state-of-the-art algorithms are actually tree-based methods, so a very exciting subject. And then we will move on to support vector machines and conclude this crash course with unsupervised learning. Now let's answer this question. What is data science? Well, data science is a field that uses scientific methods to extract knowledge and insights from data. Now, this definition may look very broad, and that's because data science is a very broad field. In fact, it encompasses three professions. So you can be a machine learning scientist or engineer, which means that you are the person who develops the algorithms. You could also be a data analyst, which is the person who answers business questions. For example, what is the product that we sold the most in the last month? That would be the job of a data analyst. Or finally, you could be a data engineer, which is the person that builds the software to gather data from different sources, because usually the data needed to solve a problem is not in the same place. So those data engineers, they gather the data from everywhere and put it in a format that can be used after by the data analyst or the machine learning engineer. Now, this crash course will mostly focus on the machine learning part because we will mostly discuss the algorithms. Now, what can you expect from this course? Well, first of all, theory. Yes, as in math equations, because theory is important in data science. You need to know how a model behaves, why it behaves in a certain way, and how it works, because understanding that is actually way harder than coding the algorithm itself, as you will see later on. Also, if your goal is to land a job as a data scientist in a company, well, you will be asked theoretical questions during the interview. So a very important part, please don't skip it. And of course, each algorithm section will be accompanied by hands-on examples in Python. So for each algorithm, we will download a dataset and we will apply this algorithm on that dataset. So without further ado, let's get started with the setup. All right, let's get you set up to do some data science. Head over to Google and search for Anaconda. Then click on the first result, which should be Anaconda, the world's most popular data science platform. Once you click on it, head over to Products and then Individual Edition. You can read more about what Anaconda is if you want, otherwise simply click on Download and it brings you here where you can select the installer which is appropriate to your operating system. Now in my case I have Windows 64, so it will be the graphical installer. If you're on Mac or on Linux, choose the one that suits you best. Once you click on it, you can download and save the file. Now I will not do this since I already installed it on my machine, but once it is downloaded, you can simply follow the instructions on the graphical installer. And once everything is done, you should be able, at least on Windows, if you hit the Windows key and start typing Jupyter with a Y, simply type Enter. And after a moment, you should see this page showing up. And that means that Jupyter is installed correctly and you're ready to do some data science. If you're on Mac, however, simply open your terminal and type in Jupyter Notebook with a space and you should be fine. Alright, now that we are set up, let's kick off this crash course with our very first algorithm, which is linear regression. We start with a simple linear regression where our target y only depends on one variable, x, and a constant. Beta 1 is then a parameter, which can be positive or negative, that characterizes the slope, and beta naught here is the constant. To find the parameters, we need to minimize a certain error function. So here the error is simply the difference between the real target, yi, and the prediction, y hat. For linear regression, we minimize the sum of squared errors. So we raise this equation to the power of 2 and add all errors across all data points. Visually, it looks like this. The red dots represent our data, and the blue line is our fitted straight line. Each vertical line is the magnitude of the error. So we want to position the blue line such as the sum of the squared length of each vertical line is as small as possible. Now you might wonder, why do we square the errors? Well, as you saw, the points can lie above or below the fitted line. So the error can be positive or negative. If we did not square the error, we could be adding a bunch of negative errors and reduce the sum of errors. It would trick us in thinking that we are fitting a good straight line, where in fact we're not. It also has the added advantage of penalizing large errors, so we really get the best fit possible. For simple linear regression, you can find the parameters analytically with these formulas, where x bar is the mean of the independent variable and y bar is the mean of the target. Now, of course, in practice, we will use Python to estimate those parameters for us. Here, you can see we first initialize the model and then we fit on x and y. And then we can retrieve both the intercept and the coefficient, as you can see here. Once you have your coefficients, we need a way to assess their relevancy. To do so, we use the p-value. This allows us to quantify the statistical significance and determine if we can reject the null hypothesis or not. In Python, we can analyze the p-value for each coefficient like this. Here we use a statistical package from Python that allows us to print out a summary of the model. Here you can see an example of that summary. So for each coefficient, you get here the p-value, which is the p greater than absolute value of t. Here you see the value is 0, but it is really not 0. However, it is so small that it appears to be 0. Once we know our parameters are relevant, we must assess the model itself. We usually use the residual standard error. Of course, the smaller the value, the better it is, since the difference between predicted and actual is small, as you can see with the equation on the screen. Also, we use the R-squared value, which measures the proportion of variability explained by a feature x. As it approaches 1, it means that we are explaining a lot of the variability in our target. In Python, we can use the same process as we did before to find the p-value using the same package. So as you can see, when we print out the summary, this is the full printout that you get from the Python package. You see highlighted in yellow the R-squared value in this example. Now from here, multiple linear regression is easy to understand, as we simply extend the model to accommodate more features. Now each feature has its own parameter, and p is the number of predictors. So in Python, we saw how to access the constant n1 parameter, and if we have multiple parameters, then we simply increase the index to get the other parameters in multiple linear regression. To assess the model of a multiple linear regression, we use the F statistic. Here, P is the number of predictors and N is the number of data points. Now again, in Python, we'll use the same package that outputs for us the F statistic. As you can see here in yellow, the F statistic for a multiple linear regression model. Usually, if f is much greater than 1, we say that there is a strong relationship between our predictors and the target. For a small data set of a couple hundred data points, then the f statistic has to be way larger than 1. So that's it for the theory of linear regression. Let's see how we can apply it with Python. So let's fire up our Jupyter notebooks. Here I have a folder called data, which contains a dataset for this exercise. So, as with any project, we start off by importing the libraries we will use. So, of course, we're going to use pandas as pd. Let's import numpy as np. Now it's time to import matplotlib, because we will use that, of course, to do some plots of our data. plot of straight lines and scatter plots. Then we're going to use scikit-learn to actually fit a linear model to our data set. Linear regression. And finally, we'll also import a stats library. So stats models.api as SM, and that will give us some very cool statistical tests to test for our predictors and model in general. And of course, we use some Python magic to plot. So let's start off by importing our data set. So data is equal to pd.read CSV. I put in the path of my data, so data/advertising.csv, and then I will specify the index call equal to 0, and that means that the first column will be used as the index column in our data set. Doing data.head, you should see the following first 5 entries of our data. So as you can see, we have ad spend on TV, radio, and newspaper, and the impact on sales. So we start off with some simple linear regression. So we will only consider the effect of TV on sales. In this case, feel free to take radio or newspaper. So I always like to do a quick plot of my data whenever possible. And in this case, because we only have one feature, one target, it is indeed possible. So I first set the size of my figure, and then we do a scatter plot. So I specify the X, which is going to be data TV, the Y is data sales, and then I specify the color. I want it to be black. Afterwards, I'm just making my plot a bit nicer. So I just specify an X label. So it's going to be money spent on TV ads, and the units is money, so just $. And then plt.y label is going to be equal. Actually, no, I do not have to put an equal sign here. I need to remove that. So remove this. All right, perfect. And now I do, this is going to be sales, and it's going to be in thousands of dollars. Perfect. Finally, I do plt.show, and you should see the following plot. There you go. As you can see, so this is our data, so the sales with respect to the money spent on TV ads. Now, maybe a linear regression is not the best model here, but let's try it anyways. So we're going to specify our feature, which in this case is only the data TV. So the values are reshape -1 as required by the scikit-learn library. And then we specify the target, which is our sales. The values are reshape -1, 1. Perfect. Now we simply call the regression model. So reg is going to be equal to linear regression. And then we will fit the model to our data. We pass in X and Y. Awesome. And with that, we can print our parameters. So we can print our constant and coefficient for TV. So the linear model is Y is going to be equal to. So first we're going to access, we're going to access the intercept first. So you intercept _0. And then we add the coefficient for X, so in this case TV, and the coefficient is equivalent to beta 1 if you looked at the theory portion of this video. So as you can see, we get a constant of 7 and a slope of 0.0475 approximately. So that's great. We have a positive slope, positive constant. It seems to make sense. So let's get some predictions and actually plot our straight line. So you can get the prediction simply by calling the predict method on X. And then we do another figure. So I'm always, again, just setting the fixed size here, not curly braces. Sorry about that. It's actually just normal parentheses. So put it the same size as before, 16.8. Then plt.scatter, we pass in X, Y, and of course the color is going to be black. So this is just going to be our data set as shown above a bit earlier. And then we add in the plot of our predictions. So same X, the Y in this case is going to be predictions, and I want it to be in blue, and I'm going to specify the line width to be equal to 2, just to make sure that we can see it. Now let's just copy the labels because it's going to be exactly the same. Let's take plt.show as well. Awesome. Let's run it. And boom, as you can see, we have our straight line plotted on our graph. That's awesome. Perfect. So let's move on to the next portion where we will assess the quality of our model. So to do so, we're actually going to use the stats library. So I'm going to re-specify again my x and my y, and we're going to fit another linear model, but using the stats library. So specify the exogenous variable as sm.addConstant x, and then the estimator is simply sm.ols. That stands for ordinary least squares. That's the method we're using. Pass in y, pass in x, and we fit. Finally, you can print a summary of the estimator, and you should see the following result. So as you can see, we have an r-squared value of 0.6. So that is not very good. Only 60% of the variability is explained. The F statistic is 312, which is much larger than 1. So it seems that our model is kind of good. And as you can see here for TV, we get the same coefficients as before. And the p-value, although probably not 0, it seems to be less than 0.05. So it means that our feature is indeed relevant in this model. So that was simple linear regression. Now let's move on to multiple linear regression. So in this case, we will consider all the features, so TV, radio, and newspaper, and see how that affects the sales. So all my x's, to define them, I'm just going to drop the sales column and make sure I dropped it on axis equals 1. So I mean, I'm dropping it only the column and not the rows. And the y is going to be the same. So data sales, dot values, dot reshape, -1 and 1. Again, I'm going to fit using scikit-learn. So the regressor is linear regression. And you call fit. So x's and y. Perfect. Now, as before, we're going to print our coefficients. So the linear model is, skip a line, and then y is going to be equal to. So let's start off by printing the constant, right? So reg.intercept underscore square bracket 0. And then the coefficients will be in the same order as in the dataset. So the first one, if I remember well, is going to be for TV. So reg.coef 0, 0. And then you multiply that by TV. Afterwards, we're going to add the coefficient. So the second one, this is not in the brackets. Sorry about that. Radio, and let's put all of this inside the brackets. Start the squiggly brackets, right? And now we're gonna add the last coefficient, so reg.coef 0, 1, 2, sorry, and let's bring this a bit to the right so you can see the code. We multiply that by newspaper. Awesome. Let's run this cell. Hopefully everything is gonna work. No, your regression object has no attribute coef. Indeed, it does not. We need to add an underscore on the coefficient of TV. So coef underscore. Awesome. There you go. There we have it. So we have 2 as a constant, 0.04, so the same slope for TV, 0.18 for radio, and negative for newspaper. That is very interesting. We have a negative effect from newspaper. So again, let's use the stats library to assess the quality of our model. So I'm just going to specify the x as np.column_stack, and then we take everything. So data TV, we're going to take data radio, right? Yes, data radio, and data newspaper. Awesome. So this is our x, our features, and the target again is data sales. Reshape -1, 1. Awesome. So again, the exogenous variable, we're going to do sm.add constant. We use x. We define our estimator, which is sm.ols, and then pass in y, pass in x. In this case, exog, right? Dot fit, and we print the summary of our estimator. And you should get the following. Awesome. Now, as you can see, the R-squared value is much larger than before. We have 0.897, so we're explaining almost 90% of the variability of the sales here. The F statistic, 570, again, larger than before, so it means that our model is pretty good, actually, to predict the sales from that. And as you can see here, all the constants and all the coefficients. Now, as you see, for the last one, we have a p-value equal to 0.860. So that is larger than 0.05. And recall that this coefficient here is the one for newspaper. So that means that newspaper is actually not relevant in our model, and we should take it out. Let's move on now to the next topic, which is classification. First, a bit of terminology. Binary classification is also termed simple classification, and this is the case when we only have two classes. For example, spam or not spam, a fraudulent transaction or not. Of course, you can also have more than two classes. For example, eye color, which can be blue, green, or brown. Now you see, in the context of classification, we have a qualitative or categorical response, unlike regression problems where we have a quantitative response or numbers. So now let's see how we can perform classification with one algorithm, which is logistic regression. Ideally, when doing classification, we want to determine the probability of an observation to be part of a class or not. Therefore, we ideally want the output to be between 0 and 1, where 1 means very likely. Well, it just turns out that there is a function to do that, and it's the sigmoid function that you see on the screen. As you can see, as x approaches infinity, you approach 1, and if you go towards negative infinity, you approach 0. The sigmoid function is expressed like this, and here we are assuming only one predictor x. For now, we stick to one predictor to make the explanation simpler. With some manipulation, you can get to this formula here. So we are trying to get a linear equation for x. Take the log on both sides and you get the logit. As you can see now, it is linear with respect to x. And most importantly, the probability is bound between 0 and 1. Now, of course, we can extend the logit formula to accommodate multiple predictors. This always gives better results since you are considering more predictors. In Python, we can perform classification using logistic regression like this. So again, we initialize the model first, and then we fit on our training data, passing the features x and the target y. Then we can get the probability that an observation is part of a class. Once we have that probability, if it is greater than 0.5, we will say that it is part of that class, so we will output 1. Otherwise, it will be equal to 0, which is what the last line of this script is doing. Now that's it for logistic regression. Let's move on to linear discriminant analysis, or LDA. Now we want to learn about LDA because logistic regression has some caveats. When classes are well separated, the parameters estimate tend to be unstable. They are also unstable when the dataset is small. And finally, logistic regression can only be used for binary classification. With LDA, you can overcome those issues because it models the distribution of predictors for each class, so you can have more than two target classes. And it does so using Bayes' theorem. Now, Bayes' theorem is explained like this. Suppose that we want to classify an observation into one of capital K classes, where capital K is greater than or equal to 2. Then we let pi k be the overall probability that an observation is associated to the kth class. Then let fk of x denote the density function of x for an observation that comes from the kth class. This means that k of x is large if the probability that an observation from the kth class has capital X is equal to small x. Then Bayes' theorem states the equation that you see. The probability of the class being capital K given capital X equals to small x is the ratio of pi k fk of x over the sum of pi l fl of x from L to K, so for all classes. This was a bit challenging, so make sure to probably rerun this section of the lesson because it is very important to understand. Now the challenge here is really approximating the density function. So we will assume only one predictor and normal distribution. This is expressed by the function that you see here. This is the normal distribution function. So if we plug this function in the formula that we saw before and take the log, we find out that we must maximize this equation. Now this is called the discriminant, and as you can see, it is a linear function with respect to x, hence the name linear discriminant analysis. When applying LDA, we need to be aware of the assumptions it makes and make sure that it applies to our situation. Here, LDA assumes that each class has a normal distribution and each class has its own mean, but the variance is common for all classes. If you add more than one predictor, which should be the case because usually more predictors gives you better results, then each class is drawn from a multivariate Gaussian distribution and each class has its own mean vector, and there is a common covariance matrix. So basically, we must use vectors and matrices instead of single numbers compared to LDA with only one predictor. In practice, this is how we apply LDA. Once we initialize the linear discriminant analysis algorithm, and then we fit it on our training data, passing the features x and the target y. Then again, we get the probability with the method predict proba. And finally, if the probability is greater than 0.5, we say it is part of a class, so we output 1, otherwise we output 0. Now that we understand LDA, QDA is fairly straightforward. The main difference is in the assumptions. Just like LDA, we assume each class is from a multivariate normal distribution and that each class has its own mean vector, but this time, each class also has its own covariance matrix. Of course, because we are talking about quadratic discriminant analysis, well, the discriminant here is expressed like this, and you see that the equation is now quadratic with respect to x, since we have two terms of x being multiplied together. Now, whereas LDA was better than logistic regression in some situations, QDA is also better than LDA, mainly when you have a large dataset, because it has a lower bias and higher variance. If your dataset is small, then LDA should be enough. Again, in Python, you should see some kind of a pattern here, because as you see, it is very similar to LDA and even logistic regression. So again, simply initialize your model, fit it on x and y, predict the probability, and if it's greater than 0.5, output 1, otherwise you output 0. Now, before we move on to the coding portion, we must understand how to validate our models in the context of classification. To do so, we use sensitivity and specificity. Sensitivity is the true positive rate, so the proportion of actual positives identified. So for example, it would be the proportion of fraudulent transactions that are actually fraudulent. On the other hand, specificity is the true negative rate. So the proportion of non-fraudulent transactions that are actually non-fraudulent. We can also use the ROC curve, where ROC stands for Receiver Operating Characteristic. We usually take the area under the curve, or AUC. That's why you probably hear about the ROC AUC. We want the ROC AUC to be close to 1. Why? Well, as you can see, we plot the false positive rate against the true positive rate. Ideally, we have a false positive rate of 0 and a true positive rate of 1, which would give an area under the curve of 1, and the curve would hug the upper left corner of the graph. As you will see soon in the coding portion, we can write a function in Python that will plot for us the ROC curve and report its area under the curve. we will actually walk through the plotting and the writing of this function in the coding portion. Now, in the case of a perfect classifier, as I said, we get an AUC of 1, and the ROC curve should look like this. So that's it for the theory about classification, logistic regression, LDA, and QDA. Let's move on to a hands-on example. All right, so let's start off with this project. Fire up your Jupyter notebooks. I have already mine open. As always, I have this folder called data, in which I put my dataset called mushrooms.csv. The link for the dataset is in the description of the video. So in this project, we are going to classify mushrooms as either being edible or poisonous, depending on different features. So you have cap shape, cap surface, cap color, etc. And I put all the possible values here at the beginning of the notebook. So let's start off by importing the libraries we're going to use. So pandas as pd, numpy as np, of course matplotlib.pyplot as plt, and also seaborn as sns. Now we are going to import sklearn.preprocessing and specifically label encoder. You will see how that will be used later on. Also from sklearn.model selection, import train test split with underscores and also cross val score. Awesome. From sklearn.metrics, we are going to import the ROC curve and the AUC, as well as the confusion matrix. Shift enter. Oh, sorry. First, we're gonna put the matplotlib inline so we can see our plots. Right. So shift enter, and now I am just going to to define a path for my dataset. So data/mushrooms with an s.csv. And now I'm just going to display the first 5 rows of the dataset. All right, so as you can see, these are our first 5 rows. We see the class, poisonous or edible, and then we see the values for each feature. So now I'm just going to do a plot to see how many poisonous and edible mushrooms we have in our dataset. So this will help us see if the dataset is balanced or not. So for that, I'm going to use seaborn. And as you can see, our dataset is fairly balanced. We almost have the same amount of poisonous and edible mushrooms. So that is very good. We're not going to have to do a lot of pre-processing for our analysis. Now I'm going to define a function that will allow us to see, depending on what feature, how many mushrooms are poisonous or edible. So for example, if I plot for the cap surface, so for all possibilities of values for the cap surface, I want to know how many of those mushrooms are edible and how many of those are poisonous. So that's going to give us a bit of intuition as to which feature helps you to actually classify your mushrooms. And that's it. So that's the function. Now I'm going to show you how you can use this function, but I am not going to run it because this will actually run for all the features of the dataset. So it's going to generate a lot of plots. So I'm just going to show you how to use it, and you can run it on your notebook if you want. So you set the hue equal to data class. So that means that you're going to have 2 colors, right? So one for poisonous, one for edible. And then you simply want to drop the class column and then plot the rest of the data. So to do that, you just do plot data, and then you pass in the hue and data to plot. So fairly simple, very straightforward. Like I said, you can run this function on your own notebook if you want to see the examples, but I will not run it for now. So let's move on to pre-processing. So you can do this by doing escape 2, by the way, and shift enter. So now I'm going to check how many null values do we have in our data sets, because we do not want any empty values. So for calling data.columns, I want to print the name of the column and then the sum of null values if they are null. So you do that by data call.isNull.sum. If you run it, that is amazing. As you can see, we have 0 everywhere. So that means that we have no null values in our data set. That's perfect. Now we are going to use the label encoder. So what label encoder will do is that it will transform our class column into 1 and 0s because we cannot work with letters. We have to work with numbers, right? So you do le.fit transform data class, and now I will show you the result, data head, and there you go. Now as you can see, the class is now 1 and 0. So either it is poisonous or not poisonous. So 1 being true, 0 being false. Then you want to one-hot encode the rest of the data set. So to do that, we do pd.getDummies, and then you pass in the data. So let's see what the result of that will be. And as you can see, now we have added a lot of columns. So we went from 23 columns to 118 columns, because now for every feature, we have either true or false. And now that is perfect. This data is ready to be worked with because we have only numbers everywhere. So let's move on to modeling. First, I'm going to determine what the target variable is. So in this case, it is the class. .values.reshape -1, 1, perfect. And then the features is going to be the encoded data. Head, drop the class column, axis equals to 1 to make sure that we drop the column. And then we're going to define a train and test set. So we do xtrain, xtest, ytrain, ytest is going to be equal to the train test split that we imported earlier. So you pass in your features, you pass in your target variable, and then you define the size. In this case, I'm going to do 0.2. So 20% of the data set will be randomly removed to use as a test set. And we're going to use the rest to train. You can set a random state, by the way, to keep the results constant. So let's apply logistic regression, our first algorithm for classification. So from sklearn.linear model, import logistic regression. Now we're going to initialize the model. So logistic reg is going to be equal to logistic regression. Now I will fit the model to our train set. So pass in xtrain and ytrain dot ravel. Now we want to get the probabilities. So yprob is going to be equal to logistic reg dot predict underscore proba, and we're going to use the test set in this case because we fit before and now we are doing probabilities on the test set, right? And now we set our threshold to 0.5, so the actual prediction is going to be np.where. So in this case, if the prediction is greater than 0.5, we're going to say it's equal to 1, and otherwise is going to be equal to 0. So this is really where we are classifying our mushrooms. So we have run that and everything is okay. You can safely ignore the warning on the screen. And now we're going to see at a confusion matrix. So the confusion matrix is actually going to show you how many mushrooms were correctly classified. So confusion matrix, you pass in y test and you pass in the y prediction. And hopefully if those are equal, you will see that we're going to have a diagonal matrix. And that is actually amazing. We have a diagonal matrix. So all poisonous and all edible mushrooms were correctly identified. So let's check that with actually another metric. We're going to use here the false positive rate and the true positive rate. as well as the thresholds, and we're going to set that equal to the rock curve. Pass in y_test and y_prob. And then the rock AUC is simply going to be equal to the AUC, and then you pass in the false positive rate and the true positive rate. So here we are actually going to use the rock curve. And as you can see, when we calculate the rock AUC, we get 1, which is again perfect classification. Now I'm just going to define a function to plot the rock curve so we can visualize it, see how it looks. So this function is going to take in the rock AUC, and here I'm just basically building the plot itself. So I'm just setting the figure size to 7 by 7. I'm setting the title to receiver operating characteristic. Then I am actually going to plot the false positive rate and the true positive rate. And I'm going to give it a different color here. I'm going to use red. We're going to give it a label called AUC. And I'm also going to approximate the AUC, basically. So this is going to give us approximated to the 2 decimal places. And then I'm going to give it a legend. I'm going to put it on the lower right side of the plot. Now I am also going to plot a straight line going through 0 and 1. This just serves us as a general guide to evaluate the rock curve. And I'm going to make this line dashed. Now I am going to define the axis, so PLT axis tight. Give some labels, so the Y label is the true positive rate and the X label will be the false positive rate. And that's it for our function. So let's actually plot the rock curve that we obtained above with logistic regression. And you should get the following. So this is actually a perfect rock curve. So it's hugging the upper left corner, and we have an AUC of 1. So that means perfect classification. So now let's move on to our second algorithm, which is linear discriminant analysis. And let's see if the results are going to be different. Of course, it cannot be better, right? So from sklearn.discriminant analysis, you are going to import linear discriminant analysis. Now feel free to pause the video and try it on your own, because we are going to basically repeat the same steps as above, only this time we are using a different algorithm. So you can always pause the video and try it on your own as an exercise. So LDA is going to be equal to linear discriminant analysis. So here I'm initializing the model. Then I'm going to fit the model with our train set. So pass in xtrain and ytrain.ravel. Then I am going to get the probabilities from the LDA model. So LDA.predict proba, and you pass in x test. And then you get the predictions, and we use the same threshold as before, 0.5. So it's actually going to be the y pro np.where y prob LDA. There you go. If it's greater than 0.5, we're just going to classify it as 1, and otherwise it will be 0. Run this cell, and awesome, everything went well. As again, you can ignore the warning on the screen. So now we're going to build a confusion matrix here. So ytest and ypred LDA. And let's display the confusion matrix. And as you can see, perfect classification again. So as an exercise, we will still build the ROC curve and show it simply to make sure that we get a ROC AUC of 1. So get the false positive rate, true positive rate, and thresholds to be equal to ROC curve. Pass in ytest and pass in the y probabilities here in this case, so yprob LDA. Now display the ROC AUC of LDA. So first you assign it false positive rate, true positive rate, and now we are ready to display it. So ROC AUC LDA, and we should get 1, and as expected, we indeed get 1. Now we are going to plot the ROC curve using the function we defined earlier. And as you can see, you get the exact same function, which is again expected, right? Because our confusion matrix was the same, the ROC AUC was the same, the plot should be the same. So again, LDA is a perfect classifier in this case. And finally, we are going to implement quadratic discriminant analysis. Again, I strongly suggest that you pause the video at this point and really try to repeat the steps that we have done before using QDA. So as always, we're going to import the model from sklearn. So from sklearn.discriminant analysis, import quadratic discriminant analysis. Now you set the model, so you initialize it, so QDA is quadratic discriminant analysis. You can always press tab, by the way, for autocomplete. You fit the model on your train set, and then you get the probabilities. Like I said, the steps are exactly the same, it's just that we are using a different model. So yprob QDA is QDA.predict proba, and you use the test set, of course. And then we get our classification. So np.where, use the same threshold. So if it is greater than 0.5, classify as 1, otherwise it is 0. Awesome. Run the cell and ignore the warning. Then we're going to take a look at the confusion matrix. So let's see if we also get a perfect classifier here with QDA. So confusion matrix, you pass in ytest and the predictions. Displaying the confusion matrix, as you can see, we get the exact same as before. So again, QDA is a perfect classifier for our data set. Now we're going to plot the ROC curve and get the ROC AUC as well. So just like before, false positive rate, true positive rate, thresholds is going to be equal to ROC curve, pass in ytest and the y probability, so yprob QDA. And then you use the false positive rate and true positive rate to get your ROC AUC. So here I'm calling it ROC AUC QDA. It's going to be equal to the AUC, pass in the false positive rate and the true positive rate. And now you can display the ROC AUC of QDA. And you get 1. Perfect, as expected. Now we are simply going to plot it to make sure that it looks like the other plots, and you know that it will and it should. And as expected, perfect ROC curve AUC of 1. Now let's talk about resampling and regularization. Resampling and regularization are two important steps that can significantly improve our model's performance and our confidence in the model. Specifically, resampling helps us validate our model, and we usually do so with cross-validation. Regularization is used to prevent overfitting, and we will cover both ridge regression and lasso. So first, let's cover resampling methods. Resampling involves repeatedly drawing samples from a training set and refitting the model on each sample. This allows us to gain more information than if we were fitting the model only once. We can also test how the model would perform on unseen data without collecting new data. That is important because a model in production will have to predict on data it has not been trained on. Cross-validation is a widely used method for resampling. We use it to evaluate a model's performance and to find the best parameters for the model. There are three ways we can do cross-validation. We can have a validation set, we can do a leave one out cross-validation, or we can use the method of k-fold cross-validation. Let's explore each one of them. The validation set is the most basic approach. We have a dataset of endpoints, and we randomly split the dataset into a training set that you see in blue and a test set that you see in orange. We fit the model on the blue set and make predictions using the orange set. This has some drawbacks because the test error rate is variable depending on which observations were in each set, since we are splitting randomly. Also, only a small subset of data is used for training, when ideally we want as much data as possible for training. So instead we could use leave one out cross-validation, or LOOCV. In this method, only one data point, in orange, is used for validation, and the rest is used for training. You repeat the process for as many times as you have data points, so in this case, n times. The error rate is approximated as the mean of errors for each run. Now, this method has the benefit of having no randomness, but it's not a viable option for very large datasets. So now we introduce the k-fold cross-validation. This is by far the most common approach. Here, we randomly split the dataset into k groups, or folds. We use the blue set for training and the orange set for validation, and we repeat the process k times. Now realize that LOOCV is a special case of k-fold, where k is simply equal to n, the number of data points. Usually we set k to 5 or 10, and like I said, this method is probably the best and the most widely used. In Python, we can perform cross-validation like this. Here we see an example with linear regression. We first initialize the model, and then we can get the mean squared error for each fold. Notice that we are performing a 5-fold cross-validation because the CV parameter is set to 5. Then we can get the mean of all errors. Now notice that we report the negative of the mean because the algorithm uses the negative mean square error as a scoring system. Therefore, we need to get the negative so that we bring it back to a positive value. Now let's move on to regularization. Models can sometimes overfit, meaning that they will not generalize well and perform poorly on unseen data. This brings me to the subject of bias-variance trade-off. On the left, the model has a high bias and low variance, and you see that it's not a very good fit. On the right, you see a model with high variance and low bias. The model is overfitting and varying a lot, and it will not give good predictions. So we want to find a middle ground and prevent the models from overfitting. And that's why we use regularization. It will help us decorrelate our model to prevent overfitting. Here we will discuss ridge regression and lasso. Note that these methods are also called shrinkage methods. We know that traditional linear fitting minimizes the RSS, the residual sum of squares. With ridge regression, we add another parameter to the optimization function. Here we add the sum of parameters squared with a coefficient lambda. Lambda is called a tuning parameter. To find the best value of lambda, we will use cross-validation with a range of values for lambda. The best value will be the one minimizing the test error. With this method, all predictors are kept. And note that this is also called L2 regularization. In Python, to use it, we first initialize the ridge model. Then the lambda parameter is actually alpha with the library that we use in Python. In this code snippet, we provide an array of different values for alpha, going from 10 to the minus 15 to 20. Then we will use fivefold cross-validation to use the best value of alpha for our model. We'll get to apply this later on during the project example. Now with lasso, we also add a new term to the optimization function, and lasso is also called L1 regularization. Here, we add the sum of absolute values of all coefficients, and we still have our tuning parameter lambda. Now if lambda is large enough, some betas will go to 0, meaning that some features will disappear, and so feature selection can be done with lasso. In Python, as you can see, it is very similar to what we did with ridge, only this time we initialize the lasso algorithm. So that's it for the theory. Now let's apply these methods in a project. Alright, let's open our Jupyter notebooks. In this exercise, we will revisit a previous dataset we used for linear regression. So I always have my data folder, and we'll use the advertising.csv dataset. So we start off by importing pandas, numpy, and matplotlib. So pandas as pd, numpy as np, and then matplotlib.pyplot as plt. And of course, do not forget your Jupyter magic so that we can display our plots in the notebook. Then I will set the path to my dataset and read in the data. So data/advertising.csv, and then you read the dataset with pandas, and we will display the first 5 rows of the dataset using the dataframe.head method. Index call is equal to 0, data.head, and there you go, the first 5 rows of our dataset. Now let's define a function that will allow us to plot the target against each feature. So as you see, the target will be sales, and then we have 3 features: TV, radio, and newspaper. So I'm going to define scatterplot and pass in feature as a parameter. Now I will specify the size of the plot to make it slightly bigger so we can see it clearly on the screen. plt.scatter, data feature, so this is the x-axis, and then on the y-axis it will always be sales because that is our target. And I will specify the color of the points. I want them to be black. I'm going to give it an x label. So on the x-axis, this will be the money spent on whatever feature we are plotting. So it will be money spent on TV ads or radio ads or newspaper ads. And then I specify a label for the y-axis, and in this case it will be our sales in thousands of dollars. Finally, we simply display the plot. So now we can run this function and pass in each feature so we can get a sense of how each feature is correlated with the target. So TV, radio, and newspaper. And once you run this cell, you should see 3 different plots. And as you can see, newspaper does not seem to be very well correlated with sales. So now let's define our baseline model and see how regularization will improve it. So first I will import cross-val score. So model selection import cross_val_score and linear regression. And these will be used for our baseline. So our baseline model will be a very simple multiple linear regression. So as a first step, we will define our feature vector. So in this case, we are only going to drop the sales column. and then we will define our target, which will be sales. So data sales dot values dot reshape -1 1. Perfect. Now we will fit the model. So first initialize it, linear regression, and then we will calculate the MSEs. So we are going to use cross-validation here, calculate the mean squared error, and then we are going to average those errors. So you pass in the model, X, Y. The scoring, we need to use negative mean squared error as required by this library, and we do 5-fold cross-validation. So this will give us 5 different mean squared errors. So then to get the mean, we simply do np.mean of those MSEs. And now we will report the average mean squared error, bring it back to being positive because remember they were negative. And so we get 3.073 approximately. So let's see now how regularization can help us improve on our baseline. So let's try ridge regression first. Regularization and then ridge regression. Perfect. We will need to import a grid search to find the optimal value for our tuning parameter. And of course, we will need to import ridge. So sklearn.model selection import grid search CV, and from sklearn.linear model we are going to import ridge, simply like that. Awesome. So we start off by initializing the model as always. So ridge is going to be equal to ridge, and now we will define a list of possible values for our tuning parameter. So in this case, the parameter is called alpha in scikit-learn. And now let's pass in a bunch of values to test, and we will use cross-validation to find out which one is the best. So we pass in 1e to the -15, -10, -8, -4, -3, -2, and then we go to 1, 5, 10, and 20. Feel free to use as many values as you want, but as a starting point, we will use these ones. So now to run our 5-fold cross-validation, we run grid search CV, we pass in the model, and we pass in the list of parameters. The scoring will also be negative mean squared error, so we keep this consistent with our baseline model, and again, 5-fold cross-validation. Now we can fit the model, pass in your feature and your target. That is awesome, and it's done. So now we can actually print out the best value for the parameters, and we can print out as well the mean squared error. So you can do that by finding the best params, and then it's going to be the best score. Exactly. So when we print this out, you see that the best value for alpha is 20. And let's not forget that our scores were negative, so let's bring it back to positive. It's 3.0726. So it is a slightly lower MSE. So now let's try out Lasso and see if we get an even better result. So at this point, you can try and pause the video to work it out on your own, as the method will be very similar to what we have done with ridge. So moving on, we're gonna initialize Lasso and set the tolerance to 0.05 so that it can converge in a reasonable amount of steps. Let's grab our list of parameters for alpha because this, I'm simply going to reuse the exact same values to test during our grid search. And then we exactly reproduce what we did with ridge regression. So Lasso regressor is going to be equal to grid search CV. You pass in your model Lasso, you pass in your parameters. The scoring method will be neg mean squared error. And again, we do a cross-validation of 5-fold. Finally, we can print out the best parameters and the best score. So this will give us the value of alpha that gave the lowest mean squared error. And of course you do that after you fit the model. Best params, print lasso underscore regressor dot best underscore score underscore. Once we run this cell, don't forget your negative. Once we run the cell, there you have it. The best value for alpha is 1, and we get a mean squared error of 3.036 approximately. And this is indeed the best score. All right, let's kick off this portion about decision trees with a bit of theory. Tree-based methods can be used for both classification and regression. They involve dividing the prediction space into a number of regions. The set of splitting rules can be summarized in a tree, hence the name decision trees. Now, a single decision tree is often not better than a linear regression, logistic regression, or LDA. That's why we introduce bagging, random forests, and boosting to dramatically improve our trees. Now, before we move on, we need to get familiar with a bit of terminology. Trees are drawn upside down. The final regions are called leaves. The point where a split occurs is called a node, and finally, the segments that connect the nodes are called branches. Here is an example of a basic decision trees, with the leaves at the bottom, and then the branches, and you see the nodes where it splits. Now let's see how a regression tree works. To create a regression tree, we divide the predicted space into j distinct and non-overlapping regions. Then, for each observation that falls in a region, we predict the mean response value of that region. Each region is split to minimize the RSS. It uses a top-down greedy approach, also called recursive binary splitting. Now, why top-down? Because all observations are in a single region before the split. And why do we call this greedy? That is because the best split occurs at a particular step to make the best prediction at that step, instead of looking ahead and making a split that will give a better prediction later on. Now mathematically, we define the pair of half planes like this, and we seek J and S to minimize the RSS of both planes. However, this may lead to overfitting, and as you can see on the right, that's why we need to sometimes prune the trees and use cross-validation to prevent overfitting. In Python, a regression tree is very simple to implement. As you can see, we import the model from the sklearn library, we initialize it, and then we fit on X train and Y train. Now let's see how a classification tree works. It is very similar to a regression tree, but instead, we predict the most commonly occurring class in a region. Also, we cannot use the RSS since we are dealing with categories, so we must minimize the classification error rate. The classification error rate is simply the fraction of training observations in a region that do not belong to the most common class. However, this is not sensitive enough for tree growing. So instead we use the Gini index, which is a measure of total variance across all classes. The Gini index will be close to 0 if the proportion is close to 0 or 1, which makes it a good measure of node purity. A similar rationale is applied to cross entropy, which can also be used for tree growing. Now in practice, we can simply import the decision tree classifier model, initialize it, and fit it on our data X and Y. Now that the basics are covered, let's move on to more advanced topics on decision trees. Bagging stands for bootstrap aggregation. We know that bootstrap can compute the standard deviation of any quantity. We also know that variance is high in decision trees since they are prone to overfitting. So bagging is a method to reduce variance and improve the performance of our algorithm. Bagging involves repeatedly drawing samples from the dataset, generating B different bootstrap training sets. Once all sets are trained, we get a prediction for each set, and we average those predictions to get a final prediction. So mathematically, we express the final prediction like this, and so you recognize that this is simply the mean of all B predictions. This means that we can construct a high number of trees that overfit, but by averaging their predictions, we effectively reduce the variance and improve the performance. In Python, as you can see, this is very simple to apply bagging. We can import the bagging classifier, initialize it, and then we fit it on our data. Now let's see how a random forest can also improve the quality of our predictions. Random forests provide an improvement over bagging by making a small tweak that decorrelates the trees. Again, multiple trees are grown, but at each split, only a random sample of M predictor is chosen from all P predictors, and the split is only allowed to use one of the M predictors. Now, typically, M is the square root of P. Now, how is that a good thing? Well, in bagging, if there is a strong predictor, it will likely be the top split, and all trees will therefore be similar, so variance will not be reduced once we average all predictions. With random forest, because we force a random sample of predictors for each split, we avoid this situation. Also realize that if M is equal to P, then it is just like bagging. Again, you see that applying the random forest algorithm is very simple in Python. Once imported, we initialize the model and pass in the number of trees we would like to use. In this case, we use 100. Then we can fit on X and Y. Finally, let's cover boosting. Boosting works in a similar way to bagging, but trees are grown sequentially. They use the information from previously grown trees. This means that the algorithm learns slowly. Also, the trees fit the residuals instead of the target, so the trees will be small and will slowly improve the predictions. There are 3 tuning parameters for boosting. The number of trees B, where if it is too large, then it will overfit. So use cross-validation to find the right number of trees. We have the shrinkage parameter, alpha, which is a small positive number that controls the learning rate. Typically, we set it to 0.01 or 0.001. And finally, we have the number of splits in each tree, which controls the complexity of the boosted ensemble. Typically, a single split works best. We also call that the interaction depth. Now, of course, I said that there are 3 tuning parameters in boosting. Usually there are more than that, but those are the 3 main ones that we can focus on when using the algorithm to improve its performance. In Python, we apply boosting like this. Now, in this module, the learning rate is the shrinkage parameter, and estimators is the number of trees, in this case set to 100, and the max depth is the interaction depth that we looked at earlier. Again, once the model is initialized, we fit it on our data. So that's it for the theory now. Let's see how we can apply this in a project. Alright, so let's get some code done. I have a notebook open here. Also, feel free to grab the dataset in the description and put it in a folder called data. And the dataset here is about breast cancer. So we are trying to identify patients with breast cancer from a simple blood test. So we start off by importing our usual libraries. So NumPy as NP, we are going to import pandas as PD. Then matplotlib.pyplot as PLT. We will also need Seaborn. And today we are going to use the function plot confusion matrix as well. This is going to be useful to evaluate our decision trees later on. Finally, you use some Jupyter magic to display your plots in the notebook. So now let's read our data set. I will simply define my data path in this case, so it is in the folder data, and the data set is called breastcancer.csv. Then I will use pandas to read the data. So data is going to be equal to pd.read.csv, and I pass in my data path. Feel free to use tab at any time to autocomplete. and we will display the first 5 rows of the dataset. And there you go. As you can see, the first 5 rows of our dataset. Perfect. Now we are going to check if our dataset is balanced, because we are in a classification problem, so I want to make sure that we don't have too much of healthy patients or patients with breast cancer in the dataset. That would make it imbalanced. So we'll use the count plot, and as you can see, the classes are fairly balanced here, so we do not need to do some crazy manipulations in this case. Now it will be interesting to define a function to make violin plots. That will allow us to see the distribution of each feature for both classes. So it can give us some intuition about the data. So for example, maybe we will see that most of the healthy controls are younger. So defining the function, we will need x, y, and data as parameters, and then I will enumerate each y. So we will define a figure. Then I will set some parameters. In this case, I am simply setting the figure size. I want it to be fairly large for you guys to see. So I will set it to 11.7 and 8.27. I know I am very precise. And then you will simply do a violin plot for each one. So sns.violinplot. X is equal to x, y is the column, and data is equal to data. That is perfect. So now in this case, the y is actually going to be data.columns, everything but the last column. So in this case, the features are actually going to be y, and x is going to be the target variable, because I want to get the distribution of each feature for each class. Now we can run the function, actually passing in our x, y, and data, and you get the following plots. So feel free to study those plots a little bit longer and get an intuition about the dataset we are working with. Now we are going to check for null values to make sure that nothing is missing. So for column in data.columns, I will print the name of the column, so curly brackets col, and then we will print the sum of null values. So that is data col.isNull.sum. Running this cell, and you see that we have no null values in this dataset. That is amazing. Now we will start some pre-processing. First, I would like to do some label encoding on the target variable so that we bring it to 1 or 0. So from sklearn.preprocessing import label encoder, we will initialize the label encoder, and then we will fit transform that on the row classification. So data classification is le.fit transform. And you pass in data classification. Now, to make sure that everything is right, we'll display the first 5 rows, and everything is right. Now, the healthy control is 0, and someone with breast cancer will have a label of 1. Now, we will split our data set into a training and test set. So from sklearn.model selection, we are going to import train test split. So our target is, of course, the classification, .values.reshape -1, 1. And our features is going to be everything but classification. So I am simply going to drop the classification column, and I'm going to specify the axis as well. Axis is equal to 1. Awesome. Now actually splitting our data set, note that our data set is fairly small in this case, so I will use a smaller test size than we are used to. In this case, I will use only 10% of it as a test size. So you pass in x, y, test size is equal to 0.1, and a random state of 42, so that we make sure that we get the same results. So now let's build our baseline model. So let's build our baseline model. It will be a simple decision tree classifier. So from sklearn.tree, we are going to import decision tree classifier. We will initialize the classifier, so then the brackets. Then we will fit the model, so call fit, and then you pass in xtrain and ytrain. And finally, we will plot the confusion matrix. So the confusion matrix will show us how many instances were misclassified. So you pass in your classifier, xtest, ytest, and I will specify that I want blue colors in this case. So it's going to be a gradient of blue. I do not want the grid, and I want to show the plot. So as you can see, we get this confusion matrix, and you see that only 3 instances were misclassified in this case. Now, I would like to show you a cool trick because you can visualize your decision tree with the function plot tree. So from sklearn.tree, you can import plot tree, and then let's see what it looks like. So you pass in the classifier, and I'm going to specify the max depth to 5, so we will only see 5 different splits. And there you see it. So you can see the top split, you can see which feature was used, what's the value of the split, and you can also check for the Gini index of each region. So that is pretty cool. Feel free to, not even pass in max depth, so you can visualize the entire decision tree if you want to. So now let's try and improve on our baseline model, and we will use bagging first. So from sklearn.ensemble, we are going to import bagging classifier. We initialize the model as always. So bagging CLF is bagging classifier. Then we fit the model. So .fit, pass in your xtrain and ytrain. In this case, you need to do .ravel. And now we will plot the confusion matrix. You pass in your classifier, pass in xtest, ytest, and again, I will specify gradient of blues to keep the plots consistent in the entire notebook. I will remove the grid and show the plot. And as you can see, we only have 1 misclassified instance in this case. So bagging is an improvement over our baseline. Now let's see how we can implement random forest. At this point, feel free to pause the video and try it on your own, as the process will be very similar to bagging, so to what we've done above. So from sklearn.ensemble, we're going to import random forest classifier. We initialize the model. So random CLF is going to be equal to random forest classifier, and in this case I will specify the number of trees. I want 100 trees. Then we fit the model, we pass in our train set, xtrain and ytrain, and then we will plot the confusion matrix. So I'll just grab this code right here, copy, paste it down, and then all I have to do is replace bagging CLF with random forest CLF. And I forgot to ravel the right train. Sorry about that. So ytrain.ravel. And there you have it. We have actually a perfect classifier with no instances that were misclassified. That is pretty great. However, keep in mind, this is a small data set. It doesn't mean that our model is necessarily very good at this point. And finally, we're going to implement boosting. So from sklearn.ensemble, we are going to import gradient boosting classifier. Gradient boosting classifier. So as we have done before, we initialize the model, then we fit it. So boost CLF.fit xtrain and ytrain, and then we will plot the confusion matrix. So grabbing the code again, copy, paste it below, and remove random CLF and paste boost CLF instead. And again, I forgot the ravel. Sorry about that, guys. Ytrain.ravel, and then you get this following confusion matrix where only one instance is misclassified, which is not better than random forest, but better than our baseline. All right, let's cover some theory about support vector machine. For classification, we have seen quite a few algorithms such as logistic regression, LDA, QDA, and decision trees. Support vector machine is another algorithm used for classification. Its main advantage is that it can accommodate non-linear boundaries between classes. To understand SVM, we must first understand the maximum margin classifier. Like I said, the maximum margin classifier is the basic algorithm from which SVM extends. It relies on separating different classes using a hyperplane. In a p-dimensional space, a hyperplane is defined as a flat affine subspace of dimension p-1. Therefore, in a 2D space, the hyperplane will be a line, and in a 3D space, the hyperplane will be a flat plane. The equation for a hyperplane is defined like this, where p is the number of dimensions. Now here is an example of a hyperplane in 2D, which is represented by the line. If an observation satisfies the equation we just saw earlier, then the point is on the line. Otherwise, it is above or below the hyperplane. Now realize that if data can be separated perfectly, then there is an infinite number of hyperplanes, but we only just want one. So that's why we use the maximum margin hyperplane or the optimal separating hyperplane to find it. To do so, we must calculate the perpendicular distance between each training point and the hyperplane. That distance is called the margin. Then, the optimal separating hyperplane will be the one with the largest margin. Here you see an example of a maximum margin hyperplane, and you see the margin illustrated by the arrows. Notice that the plane depends only on the closest points, known as support vectors, and if those points move, then the hyperplane will move. But what if there is no clear separation between the classes as shown here? Well, that's when SVM is required. As I mentioned, SVM is simply an extension of the maximal margin classifier. This time it uses kernels to enlarge the feature space and accommodate for nonlinear boundaries between classes. A kernel is simply a function that quantifies the similarity of two observations. The kernel can be a function of any degree, but of course, if the degree is greater than 1, then we add more flexibility to the boundary. Here is an example that we will implement later on during the coding portion of this section. Here the classes can be linearly separated, so it's easy enough. However, notice the outlier on the left, and we can use regularization to account for it or not, and we will see how that impacts the model. Here is another example that we will code, and as you can see here, the boundary is definitely not linear. But SVM does a pretty good job at finding a boundary and separating each class. So that's it for the theory. Now let's move on to the coding project and generate those plots ourselves. Alright, so prepare your notebooks and grab the data from the link in the description. In this tutorial, we're actually going to import 5 different data sets. So you can see me, I'm checking them right now. So x6 data 1, 2, 3, and then spam test and spam train.mat. So as always, we start off by importing all the libraries that we will need throughout this project. By the way, these exercises are taken from the machine learning course by Andrew Ng. I am simply solving them using Python here. By the way, it's an amazing course, and I will leave the link in the description if you want to check it out. I definitely recommend it. So we import numpy, pandas, matplotlib.pyplot, also matplotlib.cm, and from scipy.io we'll import loadmat, and finally matplotlib inline to show our beautiful graphs. Now I will simply define the path to all my data sets. So data path 1 is going to be for x6 data 1.mat, and then we'll simply do the same data path 2 for x6 data2.mat. Moving on to data path 3 for ex6 data 3. And I will define the path for the spam, train, and test as well. And we will use those data sets at the very end of the tutorial when we will build a classifier for spam using support vector machines. So train is done. Now data spam test is data slash spam train test, .mat. Perfect. Now we will need to write a function to plot our data. I decided to write a helper function here because we will be plotting quite often. So we will need x, y, x label, y label. We'll use pause label and neg label because this is mostly classification, right? And we'll also pass in x min max, y min, and y max. And set axis equal to none. So first we're going to set the parameters of the plot. We're actually going to set the figure size to make it nice and big for you guys so you can see it clearly on the screen. So I'm going to set it to 20 and 14. Now I will specify what will be considered as positive. So it's when the label is going to be equal to 1, and negative is of course when it will be equal to 0. Then if axis is equal to none, which by default it is, then we're going to set axis equal to plt.gca. Then we're going to draw a scatter plot, so axis.scatter. Pass in the positives. Then you pass in the y for the positives. I will specify the marker, so I want dots. So you can specify that by putting the letter O in strings. Then I will also specify a color. At this point, feel free to use any color you want. S equal to 50, and the line width will be equal to 2. And finally, the label will be the pause label, because those are the positive data points. Now I will draw another scatter plot, but for the negative samples. So it will be fairly similar to the line that we wrote above, only this time it's going to be for negative. So neg, column, comma, 0. And then again, so you pass in the y now, so x neg, colon, comma 1. The marker is still going to be a dot. This time we're going to specify another color so that we can differentiate them easily on the plot. So FFA 600, S will be equal to 50. The line width will also be equal to 2. And then you set the label equal to neg underscore label. Awesome. Now I will set the limits on the x-axis and then on the y-axis. So of course we'll just pass in the x-min and x-max, and then you do the same for the y-axis, so y-lim, and then you pass in the array from y-min to y-max. Now let's set the label for X. So set X label will be X label simply, and we'll specify the font size. I'm gonna put it to 12, and you do the same thing for Y label. So you set Y label, pass in Y label, and specify the font size as 12 as well. Then we will specify the position for the legend. So axis.legend is a box. Is a B box. To anchor equal to 1, 1, and fancy box we'll put equal to true. So let's start the coding portion by exploring the effect of regularization on SVM. And we'll start off this time with a small regularization parameter. So first, let's see what our dataset looks like. So data 1 is load mat, the data path number 1. X will be data X, and the Y will simply be data Y. And now we will plot the dataset. So we use our function plot data, pass in X, pass in Y. The label will be X and Y. Then the positive label, we'll simply call it positive. The negative, we'll call it negative. We want the plot to be from 0 to 4.2 and then from 0 to 5. And I made a mistake because it should be data 1, not data. All right, and you see this following plot. So as you can see, the positive is in dark blue, the negative is in yellow, and you see that this data set is clearly linearly separable, and you also notice this outlier on the left. So now let's see with a small regularization parameter what will happen to that outlier, if it will be classified correctly or not. So we start off by importing SVM from sklearn, and we'll set the regularization parameter to 1 for now. So CLF will be equal to svm.svc. The kernel will be linear because, as you can see, we can use a straight line to separate the classes. C will be equal to 1, and then you specify the decision function shape to OVR. Then you fit the model on your data. And now we will plot the data as well as the boundary. So here actually we can just grab this line from the previous cell because it will be exactly the same. We're just plotting the same data again. And now we will plot the boundary on top of this data. Sorry, I accidentally ran this cell. But now let's actually plot the boundary or the hyperplane. So we start off by specifying x1 and x2 to be a numpy.meshGrid, and then we pass in np_arrange. So we want from 0 to 5, and from with steps of 0.01, and np_arrange. Oh, sorry, this should not be here. This should be inside the big bracket of meshGrid. So np_arrange from 0 to 5 as well, with steps of 0.01. So I'm taking small steps here to make sure that we plot a smooth hyperplane, as smooth as possible. Then Z will be the prediction. Pass in np.c underscore x underscore 1.ravel, and do the same with x2.ravel. Then Z is going to be equal to z.reshape x1.shape. And now we are ready to plot the hyperplane. So plt.contour you pass in x underscore 1, x underscore 2, pass in z, pass in 0, 5, and the colors will be black, so B. And there is a mistake. We have a warning here. No contour levels were found within the data range, and that is because okay, here's the mistake. It shouldn't be a comma, it should be a point, so 0.5. Perfect. And you see this plot here with our hyperplane, which is a straight line in blue, and we have and you can see here that the outlier was not taken into account and is in this case misclassified. So now let's see what happens if the parameter is very high. So feel free to pause the video and try it on your own as an exercise, because the code will be very similar to the previous cell. So here we are going to use a large regularization parameter. We'll set it to c equal to 100. And actually I'm simply going to grab everything from this cell here and just copy paste it below, because the code is exactly the same. We are simply changing the value of the hyperparameter. So we don't need to import SVM again, and we'll simply use c equal to 100 and see what happens next. So as you can see now, the hyperplane shifted to account for the outlier. But in this case, we are likely overfitting, which means that the model would not generalize well. So ideally, we will go with the previous model that we built. So now let's try an example with a non-linear boundary. So SVM with non-linear boundary. So for that, we'll need our second data set. So data 2 is load mat data path underscore 2. And like before, we'll specify the x and y and plot our data set. So x2 will be data 2 x, y2 will be data 2 y. And now we will use our helper function to plot the data. So pass in x2 and y2. Again, the label will be simply x and y. For the class labels, we'll simply use positive and negative. And now we will set the limits on the x-axis, so 0 to 1, and on the y-axis, it's going to go from 0.38 to 1. And there you go. So as you can see now, clearly a non-linear boundary, but the classes seem to be separable. So let's see how SVM will be able to do that. For this example, we will use a radial basis function for the kernel. Here we must define gamma, which is a parameter that specifies how far the influence of a data point reaches. A low value means very far, and a high value means close. And you can express gamma in function of sigma. So let's define sigma as being equal to 0.1. And then gamma will simply be 1 over 2 sigma squared. So 1 over, open brackets, 2 times sigma star star squared. Perfect. Then our classifier will be equal to svm.svc. We pass in the kernel, and this time is going to be equal to rbf. So for radial basis function, gamma will be equal to gamma. We set the regularization parameter to 1, and the decision function shape will again be equal to OVR. Next, we fit the classifier to our data. So x underscore 2 and y underscore 2 dot revel. Then we will plot the data set. So again, just grab this line from the previous cell and paste it under, because we are simply plotting the same scatter plot as before. And now we will plot the hyperplane, so the actual boundary from the SVM algorithm. So again, as before, x_1, x_2 will be a mesh grid. You range from 0 to 1 with bounds with steps of 0.03. So here the steps are going to be slightly smaller because we are drawing a non-linear boundary, and again, it's just to make it as smooth as possible. And from 0.38 to 1 for y. Then z will be equal to the prediction. Pass in np.c underscore. This is actually just to stack the predictions, by the way. So x_1 dot ravel, x_2 dot ravel. Then we will reshape z. So z dot reshape will take the shape of x1. So x_1 dot shape. And now we are ready to plot the hyperplane. So plt.contour, pass in x1, pass in x2, 0.5, and then colors will be equal to blue. And now there is a big mistake. Input z must be 2D. And easy enough, I forgot to pass in z. So x1, x2, z, and then the array 0.5, colors equal to blue. And there you have it. We can see in blue the boundary that SVM predicted for us. And you see it's doing a pretty decent job at separating everything. You see you have a few points misclassified here and there, but otherwise a good nonlinear boundary. But now let's explore a situation where the data is not easily separable. So for that, we'll explore the third data set. So load mat. Data path _3. As before, x_3 will be equal to data 3x. y_3 will be equal to data 3y. And now we will plot the data using our helper function. So plot data, we pass in x3, y3. The labels will be the same, so x and y. Positive and negative for the labels. And we want to plot from minus 0.55 to 0.35 and from minus 0.8 to 0.6. So that makes the data points nice and centered. And as you can see now, there is a clear overlap between both classes. And so there is no clear boundary between each class. So this is when we need to use cross-validation in order to find the best parameters for the best boundary. So I will specify a list of possible values for sigma. So we'll go from 0.01, 0.03, 0.1, 0.3, 1, 3, 10, and 30. And we'll do the same for the regularization parameter C. So the same values, 0.01, 0.03, 0.1, 0.3, and then 1, 3, 10, and 30. Perfect. Now I will initialize an empty list of errors and an empty list for sigma and C. So for each value in sigma, and then for each value for C, we will define a classifier and we will fit it. So CLF is going to be equal to svm.svc. The kernel will be RBF again because the boundary is likely nonlinear. Gamma will be equal to 1 over 2 times each squared. And then after 2 brackets, we pass in the value for C, which is going to be each underscore C. And the decision function shape will be equal to OVR. Perfect. Then we will fit it to our data. So x_3, y_3. sigma.ravel. And we will append the errors to our list we defined earlier. So we're going to append clf.score on data 3 x val and data 3 y val dot ravel. And then we're going to append to sigma c the value for sigma and for c as a tuple. Now running this, I have a mistake. That's because simga should actually be sigma. And I still wrote simga at the very end. Yeah, right here, simga c is actually sigma c. Perfect. So the loop ran, it is finished. So now we can see what value for C and for sigma is the best. So index will be np.argmax, pass in errors. Sigma max and C max will be equal to sigma underscore C at that index. And now we can print out the values. So the optimal value of sigma is colon squiggly brackets sigma underscore max, and we'll print the optimal value for C as well. And as you can see, we get an optimal value of 0.1 for sigma and 1 for C. So now we can fit an SVM algorithm. So we set sigma equal to 0.1, gamma is going to be equal to 1 over 2 times sigma squared. Then we will pass in those parameters to our classifier. So the optimal classifier is svn.svc. The kernel will be RBF. Gamma is equal to gamma, C is equal to 1, and the decision function shape is OVR. Now we will fit our classifier to our data. So x underscore 3, y underscore 3 dot ravel. Then we will plot the data. So again, just go back up. Let's grab this line here and paste it back in our current cell. And as before, we will now find the points for the boundary and we will plot it. So x1 and x2 is np.meshGrid. Pass in np range from -0.6 to 0.4. And we'll take steps of 0.004 to make it smooth, and np range from -0.8 to 0.6 in steps of 0.004. Z is then going to be the optimal clf.predict, and we will stack the predictions. So np.c underscore. We pass in x underscore 1 dot ravel and x underscore 2 dot ravel. Reshape z dot reshape is x underscore 1 dot shape. And now we will plot the boundary. So plt on contour, pass in x1, pass in x2. Pass in z, 0.5 in brackets, and the color will be blue. And the mistake again here is I wrote simga instead of sigma. Very sorry about that, guys. Hopefully you're not making the same mistakes as I am. And as you can see here, we have our best boundary found from cross-validation with support vector machine. So it's actually not that bad. And finally, let's use SVM for spam classification for our emails, right? So spam train, we're simply going to load the data set called data path, and I called it spam train. Then spam test will be equal to load mat, and you pass in data spam test. We will set the regularization parameter to 0.1, and then xtrain will be spam train, and we pass in x. Ytrain will be spam train, and we want the column y. Then xtest will be spam test, pass in x. Ytest will be spam test, pass in y. Our classifier, so clf_spam, will be again svm.svc. We will start with a linear kernel, see how that performs. So kernel is going to be linear. The C parameter will be equal to C. We set it above. And the decision function shape will be equal to OVR. Then we fit our classifier to the train set. So we pass in xtrain and ytrain.ravel. And then we will calculate the accuracy. So clf_spam.score. And we will score against spam train X and spam train Y. Ravel. And then we will test for the test accuracy. So again, clf_spam.score, and you pass in xtest and ytest.ravel. Finally, we will print out those scores. So the training accuracy, squiggly brackets, pass in train_ACC times 100. So we have it as a percentage already. And we do the same for the test accuracy. Running everything, we have a key error for X. Yes, that's because here it should be xtest and ytest. Sorry about this little mistake. So if we run this cell now, our model is training and fitting, and you get a training accuracy of 99.8% and a test accuracy of 98.9%, which is very good. Moving on now to unsupervised learning, let's cover some theory. Unsupervised learning is a set of statistical tools for scenarios in which we have features but no targets. This means that we cannot make predictions. Instead, we are interested in finding a way to visualize data or discovering a subgroup of similar observations. Unsupervised tends to be a bit more challenging because the analysis is subjective. Also, it's hard to assess if the results are good or bad since there is no true answer. In this section, we will mainly focus on two techniques, which are principal component analysis, or PCA, and we will take a look at clustering algorithms. Let's cover PCA first. PCA is a process by which principal components are computed and used to better understand data. They can also be used for visualizations. Now, what is a principal component? Well, suppose you want to visualize n observations on a set of p features. You could do a 2D plot for each 2 features at a time, but that's not very efficient. and unrealistic if P is very large. With PCA, you can find a low-dimensional representation of the dataset that contains as much of the variance as possible. That means that you will only consider the most interesting features since they account for the majority of the variance. And therefore, a principal component is simply the normalized linear combination of a feature that has the largest variance. You see the equation here, and that should remind you a bit of linear regression. Also, this equation is for the first component. The next one will be in a direction perpendicular to the first one. And the third component would be perpendicular to the first two principal components. In this equation here, phi is referred to as the loadings. Here's an example of how you can apply PCA in Python. In this case, actually, we are trying to visualize the iris dataset in 2D. This is something that we will apply later on during the coding portion. So this dataset contains more than 2 features for each species of iris. So using this snippet, we can initialize PCA and then specify that we only want the first 2 principal components. And then you can see here that we can find the explained variance ratio and then use that to plot a 2D figure of the features of this dataset, which is what you see here. So as you can see, we can plot the transformed data and see how each species of iris are different or separable from one another. So that's it for PCA. Now let's take a look at clustering methods. Clustering is a set of techniques for finding subgroups or clusters in a dataset. This helps us to partition the data into observations that are similar to one another. An application of that is, for example, for market segmentation in the context of marketing. We will first explore k-means clustering, which partitions the data in a specified number of k clusters. And we will also look at hierarchical clustering, which does not need a specific number of clusters. Instead, we can generate a dendrogram and see the clusters for all possible number of clusters. But first, let's focus on k-means. This method simply separates the observations into k clusters, and we must provide that number. It assumes that each observation belongs to at least one of the k clusters and that the clusters do not overlap. It is important to note that the variation within each cluster is minimized. Here you can see an example of how the number of clusters will affect how the data is partitioned. Feel free to pause the video if you want to study this a little bit longer. Now, clustering is achieved by minimizing the sum of the squared Euclidean distance between each observation in a cluster. You can see the equation here of the Euclidean distance, and we wish to minimize it. To do so, the algorithm first starts by randomly assigning each observation to a cluster. Then for each cluster, a centroid is computed, which is a vector representing the mean of the features in the cluster. Then, each observation is assigned to the cluster whose centroid is the closest. The 2 steps above are repeated until the cluster assignment stops changing. Now note that k-means will find a local minimum. Therefore, it highly depends on the initial cluster assignment. So make sure to run the algorithm multiple times to see if you always get the same results. In the coding section of the tutorial, we will use k-means clustering to perform color quantization. More on that later on. This process allows us to take a picture and reduce the number of colors. So in this code snippet here, we specify that we want only 64 colors in the picture. Then we can apply the algorithm on the image and output a modified image with only 64 colors. The output will look like this. Of course, because we use k-means, we can specify any number of clusters to group the most similar colors together. So in this case, we use 64, but later on in the coding portion, we can use 10, 28, whatever number we want. Now let's take a look at hierarchical clustering. As I mentioned, the potential disadvantage of k-means is that you must specify the number of clusters, and sometimes you simply don't know how many clusters you need. This is when hierarchical clustering comes in, because you do not need to specify the number of clusters. The most common type of hierarchical clustering is called agglomerative clustering. It generates a dendrogram from the leaves, and the clusters are combined into larger clusters up to the trunk. Here is an example of dendrograms. We see the individual observations at the bottom, and they are combined into larger clusters as you move up in the y-axis. The algorithm is fairly easy to understand. It starts by defining a dissimilarity measure between each pair of observations, and it assumes that each observation pertains to its own cluster. Note that in this case, the dissimilarity measure is usually the Euclidean distance. Then, the two most similar clusters are combined, so that there are n-1 clusters. The next two are combined, resulting in n-2 clusters. And that is repeated until all observations fall in one big cluster. Now, although simple, how do we define the dissimilarity measure? Well, that depends on the type of linkage, and there are 4 types: complete, single, average, and centroid. Complete is also called maximal intercluster dissimilarity. So it computes the pairwise dissimilarities in clusters A and B, and it records the largest one. With single, it's the opposite, and we talk about the minimal intercluster dissimilarity. So here, the smallest of the dissimilarities is recorded, and this can mean that single observations are fused one at a time. Then we have average. As the name suggests, the average of the pairwise dissimilarities is recorded. And finally, we have centroid, which computes the dissimilarity between the centroids of cluster A and B. This is sometimes a problem, as smaller clusters can be more similar to a larger one than to their individual clusters, which can lead to inversions in your dendrogram. Complete, average, and centroid are definitely the most popular types of linkage. Note that the final dendrogram highly depends on the type of linkage you select. As you can see here, average and complete are quite similar to one another, but with single linkage, the dendrogram is quite unbalanced, and that's why this method is not used often. So that's it for the theory. Now, let's get coding. Let's apply what we learned in Python now. These exercises are available as examples on the sklearn website. I am simply reworking them a bit or explaining them here. The links are in the description, and the complete notebook on GitHub is also in the description down below. So we'll start off by importing some libraries. We will need NumPy. We'll also need matplotlib.pyplot as PLT. And finally, from sklearn.utils, we will import shuffle. So let's kick off this tutorial with a clustering. We will do color quantization with k-means, which is a technique to reduce the number of colors of an image while keeping the integrity of the image. So to do that, we will need from sklearn.datasets import load_sample_image, and from sklearn.cluster we will import k-means. Now, after importing our libraries, we will load the image of a flower. So the flower will be equal to load sample image, and we will pass in the name of the image. In this case, it is flower.jpg. Now we need to convert to floats and divide by 255, because colors are expressed as RGB, right? Red, green, and blue, with values from 0 to 255. So we need to normalize that so that the image displays correctly with matplotlib. So this is what we are doing here. So we convert to floats and we divide by 255 to normalize everything. Finally, we can show the image with plt.imshow, and we pass in flower. Now I have made a mistake here. The name np is not defined. That's because I did not import numpy as np. Sorry about that. So after rerunning this cell and rerunning this cell here, we finally get the picture of our flower, and this is what you should get. Now we will change the image to a 2D matrix. So width, height, and depth will be equal to original shape, which is the tuple of flower.shape. Here, d is the depth, will be 3. because as I explained earlier, each layer will correspond to either red, green, or blue. So 3 values in this case. And now we reshape it. So image array is equal to np.reshape flower, and then we'll reshape with the width times the height, and the other dimension will be the depth. Awesome. Now we will reduce the number of colors to 64 by running the k-means algorithm, where k will be set to 64. So our image sample will be equal to shuffle the image array. We'll give it a random state equal to 42 so that the results are constant whenever we rerun the cell, and we'll take the first 1000 samples. Now we will fit the k-means algorithm, and we set here the number of colors. As I said, this will be equal to 64. Then k-means will be equal to k-means, so we initialize the model. We pass in the number of clusters, which is the same as the number of colors in this case. And again, the random state equal to 42, because as you know from the theory part, k-means starts by randomly assigning each observation to a cluster. So we keep the random state equal to 42 to give the same results every time. And then we simply fit the algorithm. Then we get the indices for each color for the full image. That will be useful when we need to reconstruct the image, right? So each pixel in the 2D array will be assigned to a certain cluster, and that will help us to bring back the color and rebuild the image. So it's simply the labels, which is the prediction from the k-means. Now we need to write a function to rebuild the image. So like I said, each pixel is assigned to a cluster which corresponds to a specific color. So we define reconstruct underscore image, and we will need as parameters the cluster centers, we will need the labels, and we pass in the width and the height of the picture. So D will be equal to the cluster centers dot shape, and we take D at index 1. Then the image will be simply an array of zeros in this case, and the shape will of course be the width, the height, and the depth. The label index will start at 0. And then for I in the range of the width, and for j in the range of the height, we write that image at index ij, so this is the coordinates in the 2D matrix, will be equal to the cluster centers at labels, and that itself will be at the label index. And then we increment the label index, so plus equal 1. And finally, we return the reconstructed image. So that's it for this function. Now we are ready to display both the original image and the reconstructed one with only 64 colors. So the first plot will be the original image. So we'll turn off the axes, and then plt.title will be the original image with 96,615 colors. And then we will show the original image, which in this case is simply flower. And now our second plot, so plt.figure2, here we will display the reconstructed image. So again, turning off the axes, the title will be here we will write a string. Actually, we'll pass in a parameter in this string, so reconstructed image with n colors, because you can change the number of colors. We will do that after. And then we show the reconstructed image. So in there we will pass in our function reconstruct image, and you pass in k-means.cluster underscore centers underscore. Pass in also the labels, and you pass in the width and the height that we defined earlier, and you get the following result. So as you can see, the integrity of the image is kept. Actually, the flower itself is very similar. I would say that only the background is very different. So let's go above and change the number of colors just for fun. So let's say we want only 4 colors. So rerunning these cells, as you can see now, with 4 colors, the image is very different, but you can see it's almost like an artistic effect that you can play around with. So feel free to play around with this number of colors with yourself. Now let's work with PCA for dimensionality reduction. Here we will work with the iris dataset. This dataset has 4 features about 3 different kinds of iris flowers, and our goal is to visualize the dataset in 2 dimensions. So from sklearn.datasets, we'll import load iris, and from sklearn decomposition, import PCA. Now let's load the iris dataset. So iris will be equal to load iris. The features is iris.data. The target is iris.target. And then the labels or target names here is iris.target underscore names. Awesome. Now let's initialize the PCA algorithm, and we will specify that we want only the first 2 principal components, since we want a 2D plot. Then x underscore r is PCA.fit x.transform x. Now let's actually print out the amount of variance that is explained by each principal component. So the explained variance ratio from PCA, and you can extract this information from the PCA object itself. So it's PCA.explained underscore variance underscore ratio underscore. Running this cell, as you can see, the first principal component explains 92% of the variance, and the second one 5%. So that means that a total of 97% of the variance is explained with only 2 components. So now we are ready to plot our data set in 2D, and that data, that newly transformed data, contains about 97% of the variance of the original data set. So here we'll just specify 3 different colors to distinguish between the 3 different kind of iris flowers. So the final one will be FFA 600, and we'll set the line width equal to 2. Then plt.figure, and then for color in so for color, target name in zip, and we pass in colors. We will pass in 0, 1, and 2, and we pass in the target names. So 0, 1, and 2 here are simply the classes, right? So we'll draw a scatter plot. So plt.scatter xr when y is equal to I and 0, and then xr when y is equal to I, and 1. So this is basically the x-axis and then the y-axis. And the color will be equal to the color at this point in the loop. Alpha will be equal to 0.8, and then LW is equal to LW that we specified above. And finally, the label will be equal to the target name at that specific step in the loop. Now we will simply put a legend on our plot. The location equal will be equal to best. And we don't want any shadow. Finally, let's set a title to our plot. So PCA of iris dataset. Running this cell, as you can see now, we get this plot right here, and so you can visualize in 2 dimension a dataset that contained 4 features and 3 classes. So now you could follow up with some classifier, maybe decision trees on this transformed dataset to classify each kind of flower. Alright, so that's it for this data science crash course. I hope that you enjoyed it and that you learned something interesting. If you want more videos on this topic or videos on end-to-end data science projects, please check out my YouTube channel. Until next time, take care.